Hi, how's it going, everybody? Today we're gonna launch each other our campaign Science for All with the first season and first episode ever of Physiology for All, Physiology of the Kidney. I know there are many questions that you wanna ask me about. You may probably wanna know what's going on right here, right? But I promise you, everything is gonna be just clear as I'm actually trying to do my best here. Let's agree that we're using medical terms when it comes to medicine. In fact, I bet you know that. A medical term usually starts with a prefix, merely indicated by root, with or without combining vowel, as the letter O. And both are called combining form, by the way. Then it ends with a suffix. The combining form that we usually use when we're talking about kidneys are renal without H, of course, or it's going to be indicating the nose instead of kidney. Also, there are nephro, glomerulo for the glomeruli, and tubulo for renal tubules. Notice the letter O is the combining vowel here. And the most common suffix related to kidney is urea, referring to the condition of urine. This is called medical terminology, by the way, and we have nothing to do with it right now. But right now, let me introduce you to the main topics that we're gonna go through the whole episodes and seasons of Physiology of the Kidney. And stay tuned to know exactly what do they mean by the whole episodes and seasons. First, we're gonna have a look on the kidney functions. Then, a short introduction on the physiological anatomy of the kidney. Next, we're gonna point out some facts about our kidney before going through the steps of your information. So it's gonna be easy for you to understand exactly the physiology of kidneys. After that, you will be an expert enough, to give information about how renal tubules handle some solutes and electrolytes, sodium, potassium, glucose, water, and urea, and how urine gets concentrated or diluted. Then we will go through plasma clearance, acid-base balance, and finally acid-base disturbance. Now, what I meant that the whole episodes of Physiology of the Kidneys are distributed along 3 seasons of Physiology for All. Now, each season is followed by a more advanced or more difficult season than the previous one, and so on for the other scientific, educational, and tutorial courses of Physiology for All, or Science for All. Okay? So, you've got to pay me your complete attention in the next few minutes. No, actually an hour and half an hour. That's okay. Generally speaking, kidneys maintain internal homeostasis. We can summarize kidneys' action in 4 points. 1. Regulatory function, or as we've mentioned it, homeostasis, for water and electrolyte balance. Sodium, potassium, chloride, calcium, and bicarbonate are electrolytes present in our body. 2. Excretory function, to excrete waste product as urea, uric acid, creatinine, metabolic waste products. Drugs and toxins have got to be excreted by urine or by kidneys as well. 3. Endocrine function, aiming to regulate arterial blood pressure through renin-angiotensin system. And you need to be aware of that. Renin is synthesized in the juxtaglomerular apparatus, as we're gonna discuss about it later, to regulate erythropoiesis or synthesis of RBCs through secretion of erythropoietin hormone. Also paracrine regulation of renal blood flow through secretion of prostaglandins E and I2, and as well as bradykinins. And of course, let's don't forget about the metabolic function, aiming to regulate the synthesis of active vitamin D, which is 1,25-dihydroxycalciferol by alpha-1 hydroxylase enzyme present in the proximal convoluted tubule. And 2. Glucose. If you're fasting or starving for a long time, kidneys can synthesize glucose from non-carbohydrate source. This process is called, and I bet you've heard about it, gluconeogenesis. Gluco stands for glucose, neo for new of course, and genesis stands for synthesis. Now, backward reading from right to left will be synthesis of new glucose. Now, what you need to know about the anatomy of the kidney is that each kidney is divided from 6 to 18 loops. Each loop consists of a cortex that covers a pyramidal-shaped medulla with an outer and inner layers. A medulla drains into the renal pelvis through a renal patella. The functional unit of the kidney is the nephron. There are about 1.5 million nephrons in each kidney. Each nephron consists of one glomerulus, which is a tuft of capillaries arises from afferent arteriole and drained by efferent arteriole. Underneath it lies the Bowman's capsule and the renal tubules. Renal tubules are proximal convoluted tubule, a U-shaped lubricant with its 3 limbs, thin descending limb, thin and thick ascending limb, distant convoluted tubule, and collecting duct. You can notice that as the collecting duct passes from the renal cortex into the renal pelvis, it crosses the renal cortex and renal medulla, and for this we can divide the collecting duct into cortical collecting duct in the renal cortex and the medullary collecting duct either in the outer or in the inner layers of the renal medulla. There are 2 types of nephrons. About 85% of nephrons are cortical nephrons located in the renal cortex, surrounded by pretubular capillaries and characterized by short lobe of Henle, while the remaining 15% of nephrons are juxtamedullary, lie deep in renal cortex or near medulla. A juxtamedullary nephron is characterized by long lobe of Henle, and side by side it lies the vasa recta. Vasa recta is a U-shaped pretubular capillary that descends in the medulla with the juxtamedullary nephron and ascends in the renal cortex. As you can see, it's a relatively long capillary, so there will be a resistance of blood to flow in the medulla. In another word, the flow rate of blood in the medulla is just going to be very low. It has kind of great role in urine concentration, as we're going to discuss about it later. Okay, after you've known a tiny little bit about the basic structure of the nephrons, now is the time to have a look on the blood supply of the kidneys. The flow rate of blood in the kidneys is 1200 milliliters per minute, which comprising about 20% of the cardiac output. Frankly, I didn't know if you knew that the renal artery comes from the abdominal aorta, but now you've absolutely known about it, right? Okay, let's go back to our topic. Renal artery enters into the kidney through its hilum. After that, it will be divided into interlobar arteriole, arcuate arteriole, and interlobular arteriole. Then supplies the nephron through afferent arteriole, glomerulus or glomerular capillaries, and efferent arteriole. Finally, pretubular capillaries unite with the renal vein. That was the first part of the renal blood supply. Now, the second part is, of course, unless you're experiencing a transient state of short memory loss, you can't forget about vasa recta, can you? I mean, we've just talked about it a few minutes ago, right? Okay, now let's complete with the third part of renal blood supply, starting with a question. What are the difference between glomerular capillary beds and pretubular capillary beds? Well, glomerular capillary beds come from afferent arteriole. The pressure inside it is high, about 60 millimeters of mercury. So it acts to filter the plasma, and therefore it called the filtering or hydrostatic pressure. On the other hand, the pre-tubular capillary beads come from the efferent arteriole. The pressure inside it is very low, about 13 millimeters of mercury. It acts to reabsorb the filtrate, and therefore it called reabsorbing or colloidal osmotic pressure. Now, let's not to forget about an important structure in the kidney, the juxtaglomerular apparatus. As most of you know that it's located between afferent and efferent arteriole, just in the area of distal convoluted tubule. It consists of 3 parts. The first part is modified tubular epithelial cells called macula densa. It lies in the very beginning of distal convoluted tubule, in contact with afferent and efferent arterioles, as well as juxtaglomerular cells. Now, do you want to know what they do? Well, they act as chemoreceptors, stimulated when sodium chloride load decreases or when low. Second part is granular epithelial cells called juxtaglomerular cells, and they secrete renin. Will you just keep this information in your mind, please? Now, the last part of the juxtaglomerular apparatus are the laser cells located between afferent and efferent arteriole, and they also secrete renin. They're granular cells, by the way. I just kind of missing something here, and I'm not sure about it. Yeah. The renal tubules and renal vessels are innervated by sympathetic fibers from the lower thoracic and upper lumbar segments. Fibers supplying the renal vessels, afferent and efferent arteriole, are stimulating alpha adrenergic receptors, causing vasoconstriction of afferent and efferent arterioles as during exercise. Fibers supplying renal tubules, proximal, distal convoluted tubules, and thick ascending limb of fluvifen, trigger both alpha and beta adrenergic receptors to increase sodium reabsorption by renal tubule. Fibers supplying juxtaglomerular apparatus stimulate beta adrenergic receptor to increase renin secretion. Alright? And now it's our time to talk about your information, which needs 3 steps to be formed, by the way. 1. Glomerular filtration. 2. Tubular reabsorption or transport of water and solute from tubular lumen into the pre-tubular capillaries. And 3. Tubular secretion means transport of substances from pre-tubular capillaries into the tubular lumen. I guess you can predict now the urinary excretion rate. Just subtract the tubular reabsorption rate from glomerular filtration rate, and then add the tubular secretion rate. It's that simple. Hold on a second. Before we go any further, we need to be aware of some facts. So it's gonna be easy to understand how our kidneys work. First thing you need to know, and most of you knew, that daily volume of urine is 180 liter, while the urinary pH is 6, which means that it's actually acidic. About 95% of urine is water, while the other 5% are urinary components, as urea, ammonia, creatinine, Also, organic acids present in urine very limited amount. The major urinary organic acids are uric acid, organic acid, oxalic acid, hippuric acid. On the other hand, it could be an indication to a pathological condition called organic aciduria if it's abnormally existed or elevated in urine. Common conditions are methylmalonic aciduria, glutaric aciduria, and isovaleric aciduria, where organic acids that methylmalonic acid, glutaric acid, and isovaleric acid are respectively highly elevated in urine. Electrolytes as sodium, potassium, and chloride, as well as metabolites and hormones, are also present in urine at standard normal levels. So you also need to keep in mind that there are some components that shouldn't be in the first place in normal urines. In fact, they might be, an indication of pathological conditions, as we've said before. Glucose shouldn't be there in normal urine at any cost, and if it does, that will be called glycosuria, which is an indication of diabetes. The same thing is applied to plasma proteins, albumin, fibrinogen, globulin, and prothrombin. Plasma proteins won't be ever filtered through the renal glomeruli of healthy kidneys for two reasons. The first one, of course, their molecular weight, which hinder them from passing through the glomerular capillary membrane. But albumin, as we know, is relatively small and accordingly can escape from the renal glomeruli. And here it comes to the second and the most important reason to prevent plasma proteins from being filtered, which is the negative charges held within protein molecules, which repel them away from the negatively charged molecular glomerular capillary basement membrane, as we will discuss later. Now, if plasma proteins pass through the glomeruli and appear in urine, it would be called proteinuria, indicating a serious pathological condition. RBC is actually present in urine in a very low level, which rises in some pathological conditions as infection or injuries, called hematuria. Now, we're going to be talking as quickly as we can about the relationship between, okay, don't get me wrong, right? Between the renal tubules and the water. There's some parts of renal tubule would like to keep water inside and get rid of sodium and solutes. Okay, they're water impermeable, but permeable to sodium and solutes. So you can call them as diuretic segment, right? Volume of water becomes so large. So anyway, these segments are ascending limb of fluid film, both parts thick and thin, early distal convoluted tubule, and medullary collecting duct. Now, can you repeat them again? Quickly, hurry up. Okay. On the other hand, there are some parts of renal tubule just hit it to keep water inside and relatively impermeable to sodium. These parts are, don't forget to memorize with me, okay? Proximal convoluted tubule, descending limb of fluid film, late distal convoluted tubule, and cortical collecting duct. Now, seriously, what are they called? Hate water, keep sodium, things become concentrated. Yeah, that's right, concentrating segments. The same is applied to the relationship between the renal tubules and urea, which is a major component of urine, of course. Now, keep that in mind. The very beginning and the very end of renal tubules, I mean proximal convoluted tubule and medullary collecting duct, are permeable to urea. but proximal convoluted tubule is less or partially permeable to urea. Segments in between, I mean the lobe of Henle, distal convoluted tubule, and cortical collecting duct, are impermeable to urea. Now, isn't that simple? Fact number 4, we've actually mentioned it before, but you really need to keep in your mind that hydrostatic pressure, or HB, is the filtering pressure, while the colloidal osmotic pressure, or COP, is the reabsorbing or absorbing pressure. Now, here we come to the fact number 5, transport of molecules through the renal tubular borders. I don't know about you, but if you just thought about it a little bit, you will find out that cells of renal tubules, I mean proximal and distal convoluted tubule, lobe of Henle, cortical and medullary collecting ducts, actually have two borders. The one that faces the lumen of the tubules is called luminal or apical border, while that facing the capillaries surrounding the tubule is called basolateral border, or sometimes it's just called basal border. Now let's talk about the transport of molecules across the glomerular capillary or the glomerulotubular membranes. There are 3 glomerular membranes: capillary endothelium with a wide pores about 70 to 90 nanometer in diameter called fenestra, and it's clearly that they forbid the passage of large molecules across it. Basement membrane which has no pores within it, but its negatively charged composition of collagen and proteoglycan won't allow the passage of plasma ions. And we've actually mentioned it before when we spoke about the filtration of plasma proteins. Alright, the third layer is the Bowman's capsule endothelium. And it's made up of podocytes, about 25 nanometer in diameter each. Now, let's agree that filtrate contain all substances in plasma except 1. Protein or plasma proteins and substances bound to it, and 2. Molecules larger than 70 to 90 nanometer in diameter. Before we go down the glomerulus a little bit to the very beginning of the renal tubules, proximal convoluted tubule, I've got to tell you a secret that no one would ever have told you before. Or maybe would, I don't know. Substances are moving forcibly against concentration or electrical gradients by means of active transport. Did you know that? This is done by sodium-potassium ATPase pump, usually distributed alongside the basolateral border of the renal tubular cells, and requires ATP, as you know. So 3 sodium ions are pumped out and find their way into the peritubular capillaries. In return, 2 potassium ions are pumped into the renal tubules from the outside capillaries. Now, don't you think that I wouldn't have known that? You've already known about it. But the new thing is that pumping process increases the intratubular electronegativity to minus 70 millivolts. So secondary to this active transport, solutes that body committed to keep them within it as glucose and amino acids, take an advantage of this electrochemical gradient to escape from the tubular lumen through the luminal border of the renal tubular cells and find their ways back into the peritubular capillaries. They finally reabsorb it to the systemic circulation through the basolateral membrane of the renal tubular cells, and as you know, this process is called reabsorption. On the luminal border of the renal tubular cells, some solutes are removed or secreted from the renal tubular cells back into the tubular lumen. Also, as you know, this process is called secretion. So 2 types of transport may take place secondary to active transport, and this is very important, by the way. 1, co-transport, or as we call it, facilitated diffusion or passive transport, usually takes place on the basolateral membrane of the renal tubular cells and needs carrier proteins to facilitate the passage of molecules through basolateral and luminal borders. An example of co-transport is glucose reabsorption from renal tubules, which needs sodium glucose transport to protein SGLT2 to cross the luminal border, and glucose transport to GLUT2 protein to cross the basolateral membrane. The second type is counter transport, or as we call it, anti-port. Usually, but not always, takes place in the luminal border of the renal tubular cells, and it doesn't need carrier proteins here. And we're gonna have two examples of the counter transport or the anti-port. The first one is the sodium hydrogen counter transport, in which hydrogen ions are secreted from the luminal border to the tubular lumen in exchange with sodium ions, which are pushed into the renal tubular cells. This process is of counter transport is secondary to sodium potassium ATPase pump in the basolateral border of the proximal convoluted tubule and dick ascending limb or dick ascending loop of Henle. Another example of counter transport is hydrogen potassium ATPase pump in the luminal borders of late distal tubules and cortical collecting duct, which also secrete hydrogen ions. But you need to keep in mind that aldosterone hormone can act on the intercalated cells or eye cells located in the cortical collecting ducts to stimulate the synthesis of hydrogen ATPase, the transport proteins, increasing the number of open channels in the luminal borders, and thus control this very process of hydrogen ion secretion. So electrolytes may use leakage channels as sodium, potassium, and chloride leakage channels to move down their concentration and electrical gradients, or use protein co-transporter, which transport electrically neutral ions, for example, sodium, potassium, 2-chloride transporter protein in the dick ascending limb of loop of Henle, which transport two cations, or in which two cations, sodium, potassium, and two anions, 2-chloride, would be co-transported. In the same ways, more and more electrolytes and solutes will find their way to go in and out renal tubules through luminal and basolateral borders, as we're going to discuss about it later in details. Okay, be aware of that. Renal tubules prefer to reabsorb sodium, which unlike what we're thinking, I guess, right? And from this very fact 5, we came into conclusion that sodium is the basic electrolyte for the movement of solid through renal tubules by reabsorption, secretion, and excretion. Now, take a deep breath, because we've reached to the last fact related to physiology of the kidneys today. And we're going to be talking about how kidneys are responding to the changes in blood volume and pressure. You already know that renin is relieved by the afferent arteriole from juxtaglomerular cells present in juxtaglomerular apparatus, either with or without control of macula densa, which, by the way, relieves prostaglandins and detects concentration of sodium chloride, right? Okay, today let's agree that renin is relieved in response to 1, 2, 3, 4, 1. Decreased sodium chloride load, as we call it, osmolarity detected by osmoreceptors. 2. Decreased arterial blood pressure detected by baroreceptors. 3. Decreased blood volume detected by volume receptors. As well as 4. Some sympathetic stimulation can cause renin relief. Renin will circulate in the body to activate the inactive precursor angiotensinogen to angiotensin 1. Then a very interesting enzyme called angiotensin convertase enzyme will activate angiotensin 1 to angiotensin 2, causing vasoconstriction to all arterial blood vessels in the body. Now, angiotensin 2 will increase the arterial blood pressure by 3 different ways. Okay, these ways are: first, vasoconstriction of the entire blood vessels, as we've just mentioned. Second, will act on the adrenal gland, asking it to release the aldosterone hormone, which will act on the principal cells and late distal convoluted tubules and cortical collecting duct to increase number of sodium-potassium ATPase bomb located in basolateral border of renal tubular cells, and thus increase sodium reabsorption. It will also act on the intercalated cells located in the same parts as we've mentioned to increase or to stimulate the synthesis of the transport protein hydrogen ATPase, increasing number of open channels in the renal tubulars in the luminal border of renal tubular cells for hydrogen ion secretion, as we've mentioned, right? Again, aldosterone hormone will act on the principal cells to increase sodium reabsorption and on intercalated cells to increase hydrogen secretion, and both are located in late distal tubule and cortical collecting duct. Okay? And as a result of this cooperation, to increase the arterial blood pressure, we've named a system of these three musketeers called renin, angiotensin, aldosterone system. Actually, angiotensin does one more important thing to elevate the arterial blood pressure. It acts on the posterior pituitary gland to release ADH or antidiuretic hormone, which is also called vasopressin, and we will stop by a little bit to talk about it. In general, ADH is secreted from the posterior pituitary gland, as you've just known. There are two subtypes of ADH called vasopressin 1 and vasopressin 2. Vasopressin 1 is secreted when the arterial blood pressure drops, or as we call it, a state of hypotension, detected by baroreceptors, as you know, right? It acts on V1 receptors found in the walls of the systemic blood vessels, causing them to constrict, increasing the systemic vascular resistance, and finally increases the ABV or arterial blood pressure. Vasopressin 2 or is secreted when body fluids drop, or as we call it, a state of dehydration detected by two receptors. Osmoreceptors in hypothalamus, which detect osmotic drop, and volume receptors in the atrial walls, which are also called atrial stretch receptors, which detect blood volume and known as central venous pressure, CVP. Vasopressin 2 acts on V2 receptors found in the basolateral membranes of principal cells located in cortical and medullary collecting ducts. This hormone receptor interaction causes a series of transduction cascades, leading to insertion of aquaporin 2 into the luminal membrane. This allows the water molecules to cross it and then pass through aquaporin 3 and 4 located in the basolateral membrane of the principal cells. Then, by the effect of osmosis, water molecules will pass from the hypoosmolar renal tubules to the hyperosmolar medullary interstitium, where it's gonna be easy for water molecules to return back to the general circulation by blood capillaries, since medulla must maintain its hyperosmolarity by keeping the water away. This is called facultative water reabsorption under the effect of ADH. Okay, that's it. But there are more and more as we will talk about them next episode of Physiology for All. And as I promised, renal physiology is gonna be easy for you if you understood and memorized every single word in this very first episode. For more science, please subscribe to the following links. All of them, okay? Because each link is somehow connected with the other. Thank you for watching. Don't forget, learning never been restricted for anyone, and there is no limited time for it. Learning never ever been done. Science for all. Dina Abdulazim Waraba. Now, if you have any question from why they say, let me know and let me see. You know what? I'm gonna clear away the mystery of this question immediately. Till the next time, have a nice time. Goodbye.